supposed to do it, Dad. They want us to do it this
I don't
way.
know that way. Why would they change math? Math is math.
It's okay,
Math
Dad.
is math.
Hi Year 12, welcome back to Mathematics for your next video lesson. We're starting off today with a flashback question from the 2013 HSC on trigonometry. See if you can figure out the value of theta to the nearest degree. Pause the video and see how you go. Alright, so with this question, because we have all three sides in the right angle triangle, that does mean we can use either the sine or the cos or the tan ratio because we've got both the opposite, the adjacent, and the hypotenuse. We've got all of them. All right, so I decided to use tan just because why not? So I'm using the opposite side, which is the 81, and I'm going to use the adjacent side, which is the 108. So we have 81 over 108, and now to get from tan theta to just theta, we've got to do inverse tan, which we press shift tan on our calculator for. So we get shift tan of 81 over 108. That works out to be about 37 degrees. So if you said option B, you were correct, so well done. Okay, last lesson we were looking at sketching some of those exponential functions, and today we're going to be applying those concepts to solving problems and looking at some HSC questions. All right, here is our first one. We've got the temperature of a coffee in a cup that's left outside for X minutes is modeled by the equation temperature equals M times 0.9 to the power of X. So M is a number that we don't yet know what it is. We're going to figure it out in part A. The initial temperature of the coffee is 80 degrees, and we're asked to find what the value of M is. Now, we can actually take a bit of a shortcut here, which we're going to do a few times today. You may have remembered from the end of the last video, we had the thing at the front of the base of our exponential term. That was always going to be the starting point of our y-axis, which is going to be the same thing as your initial amount, which in this case is an initial temperature. So we can actually just read from the question and say, well, we know if we're starting at 80 degrees, the thing at the front, the capital M, that's just going to be 80. All right, we can prove this using a bit of algebra. So we can take our equation, temperature equals M times 0.9 to the X. Now it says initially the temperature is 80 degrees. So when X, which is how long it's been left outside for, when X is 0 minutes, we get a temperature of 80. So we put that information into our equation. So when X is 0 minutes, temperature is equal to 80. So we have 80 on the left-hand side equals capital M multiplied by 0.9 to the power of 0. Now, do you remember what anything to the power of 0 is? It's not 0. The answer is always 1. Anything to the power of 0 is 1. So on the right-hand side, you've got M multiplied by 1. So you've got M, and so we get 80 equals M. There you go. Or like I said, the shortcut that you can use, which we are going to use a couple times today, is that the thing at the front that's multiplying is always your starting value, okay? All right, now we have our equation, we have the value of M, and now we're asked to sketch the relationship over the first 10 minutes. So we'll be given an axis, and we've got to fill it in with a curve, which means we need to do some values. So of course we need a table of values, like this. Let's go from 0 up to 10 in increments of 2. We're going to substitute these 6 values into our equation and get values for temperature. All right, I encourage you to pause the video and put these 6 numbers into this equation and see what you get as your 6 answers. All right, if we did the same thing, we're doing a bit of rounding just because I don't have time to write a lot of decimals, and obviously sketching curves is not going to be perfectly accurate. We're just going to go close enough's good enough. But these are our approximate answers for 0, 2, 4, 6, 8, 10. Now we are going to plot these values onto our axis, and we're going to line them up, and we're going to get a curve looking something like this. All right, so yesterday we saw that when the number, that's the base of the power, when that's bigger than 1, you have an exponential growth, which looks like something that's shooting up really fast. This one, the base of the power, is a number that's less than 1, and that's why each time we are decreasing, and this is called decay. So this is actually not an exponential growth question, this is an exponential decay question. The temperature of the coffee is starting at 80 and it's gradually decreasing until it gets down to close to 0. All right, so there is our relationship sketched. Now we've got a couple of questions using this sketch. We have estimate when the temperature is 50 degrees. So the accuracy of this answer relies on us doing a pretty decent sketch, which hopefully we've done. Mine looks pretty decent. So we're trying to estimate the value of x, which is time, along the x-axis. We're trying to estimate the time that corresponds with a temperature of 50. So temperature is our y-axis. We're seeing where does the 50 hit our red line, and I'm going to see where that red line hits the x-axis. So we can do a couple of dotted lines like we did last time. So 50 hits about there, and then we draw a line vertically down. And it looks like about 4.5, maybe 4.4, but we're going to approximate and say roughly about 4.5. All right, so 4.5 corresponds with a temperature of 50. Now, question D is a bit of a strange one, which you do actually see in a few HSC questions where they ask you to use guess and check to answer a question, which is strange because normally trial and error is our sort of plan D, but for this question, it's our plan A. Question is, use guess and check to find after how many minutes the temperature will pass 10 degrees. So from our graph, the first 10 minutes saw it go down to about 27, 28 just here. We wanted to say if this graph kept going further and further to the right, how long would it take for this red line to get down below 10? So we can see it's clearly not going to be the first 10 minutes. It might be 20, it might be 30. We don't know. We've got to guess and check using a bit of algebra. So what we're going to do is we're going to take our equation up here, which we figured out before. Okay, the t equals, it was 80, 0.9 to the power of x. We are going to guess a value of x and see if it gets us close to 10 degrees. All right. Like I said, we're not going to put in 10 because 10 clearly isn't going low enough. We want to see it going further to the right and putting a number bigger than 10. So the first one I checked was, well, it could be after 19 minutes. So I did 80 times 0.9 to the power of 19. That worked out to be 10.8, which is pretty close to 10 degrees. So I wasn't too far off, but we're not quite there. We need to be below 10 degrees. So why don't we check the next one? Let's sub in 80, 0.9 to the power of 20. And what do you know? 9.7. So between 90 and 20, the value of the temperature of the coffee goes below 10 degrees. So 20 is going to be our guess based on our checking. So after 20 minutes, this red line is going to go below the point where the y-axis is 10. All right, cool. So that's guess and check. Let's move on with the next one. This is an example from the 2016 HSC paper. It's talking about the mass M of a baby pig at age X days. So very similar to what we just had. We've got, last time we had temperature and minutes. This time we have mass and days, but it's the same idea, okay? We have mass equal to capital A, which is a constant, it's a number, multiplied by 1.1 to the power of x. And they've already graphed the equation for us. They've done the hard part for us. We just need to answer some questions about this graph and about this equation. First question is, estimate the weight after 10 days. And so for that, we are just going to use our graph. So after the 10th day, like we did last time, we're going to draw a dotted line and see where that hits our curve. And then if we go across to the left, it lines up pretty closely with 4 kilograms. So 10 hits the curve there, across to the left, pretty close to 4 kilograms. That's going to be our estimate, or if we wanted to be a bit more precise, we could say 3.9. But anything around 3.8, 3.9, or 4 would get the marks. Like I mentioned in the previous video, for questions like this, you don't have to be exact. There's going to be a bit of room for error that's still going to get you the full mark answer. Question B is find the value of A, which is the thing out the front of our base for our exponent. So if we remember what I said last time, we can use the shortcut or the straightforward answer and just say, well, the value of the thing at the front is going to be where your curve starts from the y-axis. It's going to be your y-axis intercept. And where is this black line starting on the y-axis? It's starting at 1.5. So straight away, without any maths, with just a bit of content knowledge, we can say that's easy. The thing out the front is our starting point, which is 1.5. Beautiful. Now, part C is calculate the weight after 30 days. Now, because our graph is only graphed for the first 14 days, we can't use it for 15 and above, which is why they've asked us to calculate, which means we've got to use our equation right here. So we have mass is equal to A, which we've figured out is 1.5. So we've got 1.5 multiplied by 1.1 to the power of days. So we have this. We're just going to make the x the number of days we want, which for this question is 30. So we're doing 1.5 times 1.1 to the power of 30 days. that works out to be around 26.2 kilograms. So if we took this x-axis across another 16 spots, we would see this line going up to a height of around 26.2. Okay? All right, and now for part D, it's asking by what percentage is the pig's weight growing each day? Now, in the 2016 HSC, this question was answered, this last part, question D, was answered correctly by very, very few students. What percentage is the pig's weight growing each day? Well, let's think about what's happening with this equation right here. We have A, which we said is 1.5. We have 1.5 multiplied by 1.1 to the power of x. So think about it. If this was after 1 day, we would have 1.1 multiplied by 1.1. If we were looking at 2 days, we would have 1.5 multiplied by 1.1 squared. So it would be multiplied by 1.1 and then multiplied by 1.1. I want you to think about if you're multiplying a number by 1.1, by what percentage is that increasing it? If you're multiplying a number by 1.1, what percentage increase is that? Well, if you're multiplying it by 1, you wouldn't be increasing it. So multiplying by that extra 0.1, which is an extra 10%, means you have increased it by 10%. So the simplest answer is just the fact that multiplying anything by 1.1 is going to increase its value by 10%, and that's the answer, which very few people got. So the repeated multiplier, which is the base of our exponent, base of our power, is times by 1.1, which means you are increasing by 10%. All right, and on to the last one. This is a recent one from the 2020 HSC. Again, it's pretty tricky, but there are a few tricks that are going to make it a bit easier for us. This isn't the exact question, this is slightly adapted, but it's very similar. We have the graph showing the number of bacteria, which is the y-axis, at time and minutes. So this time across the x-axis is our time, and across our y-axis is the number of bacteria. The initial amount of bacteria is 1,000, which we can see right there, starting at 1,000. Okay, first question, a nice easy one marker. Find the number of bacteria after 40 minutes. So have a look at this graph and see what it's trying to tell you after 40 minutes. Well, 40 minutes, once again, we'll draw our dotted line up to the curve and we'll see where that is on the y-axis, and it's pretty much bang on 4,000 bacteria. And that's your answer. After 40 minutes, we have 4,000 bacteria. Okay, for question B, we have the number of bacteria can be modeled by the equation. So here's the equation of this line. They're just not telling us what A and B are. So question B is asking us to find the value of lowercase b, and then in question C, in part B, we're finding capital A. Then we're going to worry about B in part C, which is a very confusing way of saying it. Okay, so question B, again, let's think in terms of our shortcut that we've used twice already today. The thing at the front that's multiplying your base. What does that correspond to on your graph? Well, if you're listening, I said that the thing at the front is always where your y-axis begins, which is right here. Your y-axis intercept is 1,000, which means the A out the front is just 1,000. And so that simple little trick that we just said has answered 3 questions today that are really common HSC questions, as we're seeing. So it's a trick that's really useful to remember. The thing at the front multiplying is your y-intercept, where your graph starts on the y-axis. Okay, now part C is the really tricky part that a lot of people in 2020 had problems doing accurately. It is pretty confusing. It says use guess and check to find an estimate for the value of B. So we've got our equation right here. We know what A is. We're trying to figure out what B is. Okay, so the way we're going to do this is we're going to use our equation with values that we've already been given in part A, which is that after 40 minutes, so when the n value is 40, the number of bacteria, which is the y, is equal to 4,000. So I'm going to rewrite this equation. I'm going to make the y equal to 4,000. I'm going to make the n, which is the number of minutes, that's going to be 40, because we know that these two correspond from the graph. So we know that this 40 works with this 4,000. We have the value of A from part B. We've figured out from the graph that the capital A is 1,000. And now we have this equation, and we are trying to figure out what B is by, like we did before, we're just going to guess a number and then refine it. Okay, guess and check. So we're going to guess a value for B. We're going to chuck it into this equation on the right-hand side, and we're going to see if it's anything close to 4,000. If it's not, we'll have to refine our answer. All right, let's start off with a guess for B. Maybe we could guess it's going to be 2. Well, let's check. 1,000 times 2 to the power of 40. If you put that into your calculator, it is a very, very, very big number. It is way bigger than 4,000. So 2, as a guess, is way too big. So next I brought it down and I said, well, if it's not 2, maybe let's do 1.2. So just above 1. 1,000 times 1.2 to the 40 worked out to be almost 1.5 million, which is much bigger than 4,000. So we are still way too big. So this number needs to be smaller. All right, let's try 1.02. So 1,000 times 1.02 to the 40. That works out to be 2,208, which is actually too small. So we know it's not as small as 1.02, but we know it's not as big, it's not anywhere as big as 1.2. So we're going to make this guess a little bit bigger, and we're going to try and get close as we can to 4,000. So let's up it a little bit and let's do 1.03 instead of 1.02. That gets you an answer of 3261. So we're getting closer, but we're not quite there. Let's increase this guess a little bit more. Let's go 1.035. Now we're getting really, really close. We've got 3,959, and remember we're trying to get 4,000. So I'm just going to make this a little bit bigger. I'm just going to go for 1.0353. That gets us to only 5 away, so that's close enough for it to say, look, it's not 4,000, but we're very close. This right here is a very good guess for the value of B. That's going to be good enough for us today. So we're going to say our estimate of the value of B in this equation is 1.0353. So yeah, pretty strange question when the exam actually tells you to use trial and error to find an answer, but trial and error is a very valid way of finding an answer. It's just usually not the quickest one. So there is the answer to the question. All right, there's some more practice for you guys to do in exercise 8B. Question 1, 3, and 4 are recommended. And thanks for watching. I'll see you in the next lesson. Thank you very much.